Hello everyone. Today we'll be solving the Ethernaut's forger challenge. This is another interesting challenge that has to do with digital signatures, and in particular it explores a compact way of encoding the RS and V value of a digital signature. Let's take a look. So we're told that we have a token printer and it's an ERC20, and we are told that we're given one golden signature that's good for 100 shiny new tokens. And the team insists that the pass is single use and it's perfectly safe, and our goal is to make the total supply greater than 100 tokens. So if we take a look, so we see that we have an ERC20 and we have a mapping of already used signatures, and we see here that we get the signature and we get all of the information that's encoded into this signature. And we have only one function, which is public, and it takes in a signature. It takes in these values. And first of all, it requires that the signature is not already used by this mapping. And then it gets a message hash with these inputs, and it uses the correct library, ECDSA, to recover, or basically do ECDSA recover to make sure that the signature is valid and that we can basically extract the owner from that signature. So this is the regular signature verification process. And then if everything passes, we update the mapping and we mint. How can we exploit that? Well, let's first of all, as usual, paste everything into Remix. So let me just take that and open a Remix IDE. I will call my contract forger.sol. So let's paste that in, and as usual, adjust the compiler. And for this particular challenge, it's actually important to look at the version of these, well, in particular ECDSA contract here. So if I simply search for ECDSA, or let's say the one that's on Open Zeppelin, so this is basically the up-to-date version. But instead of this one, we actually see that we are using version 4.6. So if I just duplicate this tab, and if I actually go to the main branch, and I will, right now we're on the master branch, I'm just going to choose 4.6, and I'm going to go into contracts. I'm going to go into utils, cryptography, and ECDSA.sol. And in particular, in the original one, if I look at the try recover function, which takes in a hash and a signature, I see that here the signature has to be of length 65. Otherwise, we return basically an error. Whereas in the older version, the same sort of try recover function actually accepts signature's length of 65 and signature length of 64. And and we're told here that we can actually consult EIP2098 to have more details on this encoding. And in particular, we are told that, you know, the usual encoding where we have RS and V parity, so these are three values, and they take in usually 65 bytes. And this requires 96 bytes to when you have to align it with 256-bit words. And since the last piece of information, which is the yParity, usually only takes 1 byte, that's quite wasteful. So this is why compact signatures were introduced. And in particularly, they say two key observations here that are required is that first of all, yParity is always either 0 or 1. Of course, it's only two values. And because we are also preventing signature malleability with the S parameter, the top bit of the S parameter is always 0. So meaning that that top bit is not actually useful for the encoding, and we can use this top bit parameter, this top bit of the S parameter to store the yParity. And so this top bit will be 1 if yParity is 1, and 0 if yParity is 0. So this is what we will use, and this is what this version of the contract is actually using. So if the signature length is 64, this try recover will use the compact recover method. Like it will try to recover the V value from the top bit of the S value. And if the signature length is 65, we just do the regular thing and we use 3 words instead of 2. And for our contract, what it means is that, well, it means that we can encode the same signature in 2 different ways, which means that it's going to give us 2 different Ketchak 256 values, which means that we can actually use the same signature twice and mint 200 tokens instead of 100. So this is the outline of the solution. So let's just now go ahead and take a look. But of course, let's see here. So this is 4.6 contracts. I'm just going to update my links. So here, oops, here and here. Yeah, there we go. So now we are compiling and we're using this older version of ECDSA. And let us have a contract, and we'll call it the attack contract. And we'll have a function attack. And we'll make it external. And we will have a bytes memory sig1 is going to be equal to some bytes, and we're also going to have a sig2. So we're going to have 2 different signatures. And let's go ahead and maybe get this signature value. So our first signature is just going to be the regular signature. And if we just analyze it very, very quickly, and maybe if I just try to split it. So we have this last bit, which is the V value, and I'm going to try and basically split it in 2. So like this, and yeah, there we go. So this should be the correct split. So as we can see here, this is this is the R value, and this is the S value, and this is the V value, which is 1C. And how do we actually do this? So we need to analyze this first. Excuse me. We need to analyze this first byte, or not even byte, but this first 4 in. Yeah, actually, I think we would like to use the terminal here. I would simply like to cast. We can do to base. So we would like to know what 40 looks like in base 2. So yeah, I would like to know what it looks like in base 2, and we see that there's actually 7 values here, but we obviously want 8 values in binary. So really, what we're looking at is here. So we see that indeed the top bit of our S value is 0, but we need to set it to 1. And let's just cast to, I guess, hex. So we see, of course, this would just be 0xC0. And so this will be our second signature. So we just need to replace this 4 with a C. So it's going to be C0. And there we go. And we don't need the V value because the V value is already encoded. So we're just going to take this entire thing, maybe just even remove it and put it here. And so this is going to be our compact encoding of the same signature. And let us perhaps receive a target, or let's just receive a forger, or I guess just an address forger. And then we're going to do forger dot, I think the function was create these new tokens. And let's go ahead and paste all of the parameters that we need. So here we're going to have sig1, and so we have all of the values. So the receiver is this value. The amount is 100 ether. And of course, we don't need this. The salt we are given is this. And the deadline is this. So we can call this create new token signature. And here I can just copy paste it. And we can replace sig1 with simply sig2. And this is pretty much it. So this will mint 100 tokens twice. So I can just compile this, and we can deploy this on Sepolia. So I will do Sepolia testnet and deploy the contract. I will confirm, and I will right away get my instance address. So this is going to be our forger target. So I have the attack contract here, and I can paste out my instance address, and I can press attack. I can confirm the transaction, and again, once we do that, we're pretty sure that we have passed the challenge because our attack function mints twice using basically the same signature, and the only thing that the challenge required is to, was to make the total supply greater than 100 tokens. And we can even probably check this with total supply dot to string, and we see that we indeed have 200 tokens. So we can be fairly confident that we have passed this challenge. And yeah, again, it was a pretty easy challenge, but at the same time, I think it's very informative for those of you who didn't know how to compactly encode 65-byte digital signatures. I think this challenge is very educational. So thanks again for watching, and I'll see you next time.